Hello, this is Professor Hester. In this video, we'll discuss how Ethernet frames are built using ARP and neighbor discovery for CCNA networking. First, we'll learn how ARP and neighbor discovery are used to get information to build Ethernet frames. Then we'll compare the ARP protocol to the switch frame forwarding process. So let's get started by looking at ARP and neighbor discovery. When devices build an Ethernet frame, they need the destination MAC address. But how do they get it? Devices discover the MAC address of their neighbors through two different methods. In IPv4, they use Address Resolution Protocol, or ARP. This is a Layer 3 protocol. It may seem like a Layer 2 protocol since we are focusing on MAC addresses, but we need to use the Layer 3 IP address to get it. The device needing the address sends an ARP request that says, "Who has IP address 192.168.1.10?" The device with that IP address responds with an ARP reply with its MAC address. Each device has an ARP table where it stores the IP to MAC address mappings. In IPv6, a different process called neighbor discovery, or ND, is used. This runs over ICMPv6, which is similar to what is used for ping. We'll talk more about that after we look at ARP. Using Wireshark, we can see inside the ARP request and reply. PC at 192.168.1.147 needs the MAC address for 192.168.1.1 to build a Layer 2 Ethernet frame. It sends an ARP request with "Who has 192.168.1.1? Tell 192.168.1.147. We can also see in this message's header that it is sent as a broadcast message to an address of all Fs. The next message is the ARP reply. 192.168.1.1 announces it has address 70:6E:6D:8D:76:A1. Let's look at an example. PCA and PCB are on the same network. PCA wants to send a message to PCB. Since it is on the same network, PCA won't send it to its default gateway. It can be sent directly to PCB. But first, PCA must build a Layer 2 frame with PCB's MAC address as the destination. PCA looks up PCB's IP address in its ARP table, but does not find it. Next, it sends an ARP request to get PCB's MAC address. The ARP request needs to go to every device on this network, so the destination MAC address and the request is all Fs. Switch S1 receives the frame on port F01. Since the destination is the broadcast address of all Fs, the switch doesn't need to look it up in its MAC address table for forwarding the message. Instead, the switch floods the ARP request out all ports except the ingress port F01. Each device except PCA receives the ARP request. PCB sees the ARP request and looks at the IP address. It notices that it matches. PCB sends an ARP reply to PCA's MAC address, AAAA. It uses its own MAC address, BBBB, as the source MAC address in the frame. It forwards the reply to the switch. The router also sees the ARP request. Since the IP address doesn't match, it discards the request. The switch forwards the ARP reply to PCA, and PCA adds PCB's MAC address to its ARP table. The entry shows the paired IP address with the MAC address. Now that PCA has the information it needs, it builds a frame for PCB with a destination MAC address of BBBB. We can view the contents of an ARP table on a device. However, dynamic entries can time out and we will only see recent entries. To view the ARP table on a PC, issue command ARP-A. To view the ARP table on a switch, issue command show IP ARP. ARP has a few security issues. First, ARP poisoning occurs when a rogue device sends an ARP reply with its own MAC address to receive another device's IP traffic. Also, ARP spoofing occurs if a device changes its own MAC address to match another device's MAC address. In each case, the device receiving the bad ARP reply adds the wrong MAC address to its ARP table. One mitigation technique uses dynamic ARP inspection, or DAI, to build a table of valid IP to MAC address mappings. You will learn how to configure this later with DHCP snooping. IPv6 uses a different process using the ICMP v6 protocol. Instead of sending ARP requests, devices send neighbor solicitation or NS messages. This message is not sent to a broadcast address, but to a special solicited node multicast address. The target of the NS message replies with a neighbor advertisement or NA message. Devices store the neighbor discovery information in a neighbor cache. Now that you have learned about frame forwarding and ARP, let's compare both of these processes. Each of these processes are used on local networks. It's easy to confuse them, but they have different purposes. ARP is used by end devices that need a MAC address to build a frame, whereas the MAC address table is only used by switches. It is used to know which port to forward a frame out. Here is a summary of the two processes that learn and use MAC addresses. To create a layer 2 frame, we need to know the MAC address associated with the destination IP address. The Ethernet frame header has both the source and destination MAC address. After we learn the MAC address, we store a mapping of it with its associated IP address in the ARP table. These MAC addresses are learned through ARP. The other process that learns MAC addresses is by switches when forwarding traffic. They need to know which port to use for a destination MAC address to forward the traffic. Switches store mappings of MAC addresses for each port in the MAC address table. Switches learn MAC addresses by looking at the frame header on incoming traffic and storing the source MAC address. Now let's review what we discussed in this video. How does a device get the destination address's MAC address? For IPv4, ARP, or Address Resolution Protocol, is used. For IPv6, Neighbor Discovery, or ND, is used. Which devices receive an ARP request? All devices in the network receive the message since it is sent to the broadcast address of all Fs. This is also known as the network's broadcast domain. How do you view the ARP table on a PC? You can view the table by issuing command ARP-A. And here is a summary of the quiz answers. I hope this video helped you learn about how Ethernet frames are built using ARP and neighbor discovery by learning MAC addresses from other devices on the local network.